Chapter 7's all been about integration techniques. Okay, the technique of use substitution, both with and without bounds. The technique of integration by parts, both with and without bounds. The shortcut of tabular integration. Now we're going to look at how to integrate a technique that's useful in a differential equation. So we need to remember what differentials are. A differential by definition is a piece of a derivative. So differentials are dy and dx separately. Right? dy and dx together make what we call a derivative. But dy and dx separately are what we would call a differential. And when you have a differential equation, it likely does not pass the vertical line test, so it's not a function. Okay, diff EQs is sometimes what the abbreviation for it. Okay, diff EQs are likely not functions. Okay, they fail the VLT. If you're going into engineering or thinking about it, you will take an entire class dedicated to differential equations. That's what it's called, differential equations. It'll be a whole semester worth. Okay, we're going to do like 2 days just to get us started on differential equations. Okay, there's so much more to learn about them because most functions in real life, or most things in real life, are not functions. They don't pass the VLT. Because this is incredibly important for modeling in engineering or architecture or things like that. The technique that you're going to walk out of here with is called separate and integrate. This is not, you're not going to find this in the book. It's just a little rhyme I made up to help you remember the process. Sort of like integral over interval. Usually when I say that, that's enough to get you going. So hopefully, separate, I think I'm spelling separate wrong. I always mess up. No, it is A. Sometimes then I change it to E, and then that looks wrong too. Okay, separate. Separate and integrate. All right, let me show you what that means in a process of a differential equation. All right, so you'll be given dy dx, which is a derivative, being equal to negative 2xy squared. Okay, that clearly fails the vertical line test because you've got x and y on the same side. The instructions are solve for y. In other words, get this into a y equals equation. And so you want to separate all x variables to one side of the equation, and you want to get all the y variables to the other side of the equation. So the first thing we do would be to move the differential dx. So that's going to give me dy by itself equals negative 2xy squared with a dx on the end. Okay, the separation has begun. I've moved the dx to the right side of the equation. But I have a y squared that's there, and I need to move that to the other side of the equation. So in other words, separating all variables that are not similar to each other. And so I'm going to move y to the negative 2 to the other side. That's the same thing as dividing by y squared. So now I have created the separate part of the process. All y terms are on one side, all x terms are on the other. Once you've completed that, you move into the integration phase, and you're going to integrate on both sides. So you're going to have an integral on each side of the equation. And you're going to follow the rules for integrating each side separately. Y to the negative 2 follows the rules of becoming y to the negative 1. And then there's a negative for the chain rule, plus a constant. I'm going to call that C sub 1 right now. On the right side of the equation, negative 2x integrates into negative x squared. And it also has a constant, which I'm going to call C2. So I have a constant on both sides. So my separate process was first, my integrate process is complete, but now I just have to solve for y, which means get y by itself. So what would you do first to get y alone? What would you do to both sides? Say that again? Sure, subtract C1, right? Yes. Okay, all right, so we're going to subtract C1, which is a constant. And when you take one constant and subtract a different constant, what do you get? Still a constant. So we're just going to call that plain C. Okay, now I want to get, keep getting this alone, so I'm going to divide by negative 1. So I'm going to get y to the negative 1 equals x squared. And this bothers people sometimes when it's still plus c. It's like, oh, you just divided by negative 1. Why is it still plus c? Because it's still a constant. And when you add or subtract constants or multiply constants, it's still a constant. And so we write plus c. But I still don't quite have y alone. And so I want to raise both sides to the negative 1 power. So I say, okay, I'm going to use yellow. This raised to negative 1. That raised to negative 1. So on the y side, negative 1 times negative 1 is just 1, so I have y by itself now. And on the other side, I have the quantity x squared plus c raised to the negative 1, which is 1 over the entire quantity x squared plus c. And I now have y by itself, and that's the solution to this differential equation. I just got y alone. Okay, please be careful. This is not the same as 1 over x squared and then plus c out here. That is not the same thing because the plus c is in the quantity as being raised to the negative 1. Nor is it the same as this. That is not the same either. X squared plus c as a quantity raised to the negative 1 doesn't mean just take the reciprocal of each piece. Okay, so make sure you're writing that correctly, that it would be 1 over x squared plus c together under the same denominator. Okay, let's try another one. Okay, given the differential equation or the derivative dy dx equals x over 2y, and given 2, negative 3. Now you're given an extra little bit of information, but you're still asked to find y. What's the purpose of that 2, negative 3? It's going to help you to find c. Okay, we separate and integrate. And so I'm going to cross multiply here so that I can separate. So I'll have 2y dy cross multiplied, and on the other side I'll just have x dx. So this was pretty easy to separate using cross multiplication. Now I will integrate. So I integrate both sides. The integral of 2y dy is y squared plus your first constant. On the other side, the integral is 1/2 x squared plus your second constant. Now you want to find c before you find y. So combine the c's together, subtract c1 to both sides, so you just have 1c. Okay, did you hear me? Find c before you find y. Don't find y first and then try and find c. It's so much easier, trust me, in the long run, if you find c before you find y. So we've got 2, negative 3. Those are the values we're going to plug in for x and y. And so negative 3 goes in for y, and 2 goes in for x. So we have 9 equals 2 plus c, so c is 7. Once you have your c, then you can go about the business of finding y. So I'm now to the part where y squared equals 1/2 x squared plus 7. What do I do to both sides to get y by itself? Square root. What goes in front of every square root? A plus or minus. So this is the plus or minus square root of the quantity 1/2 x squared plus 7. Now this fails the VLT because a plus or minus square root looks like that. It has an upper piece and a lower piece. So this fails the VLT right now. So what we need to do is figure out which part to keep. Are we keeping the upper half or are we keeping the lower half? Well, you go back to your initial condition. Look at what quadrant your initial condition is in. 2, -3. What quadrant is that? Quadrant 4. So since 2, -3 is in quadrant 4, our solution has to go through quadrant 4. And so our solution is only the negative part of the square root so that we satisfy and go through the initial condition without failing the VLT. Okay, any questions so far? I'll keep going. Okay, how about something like this? Given another derivative, dy dx, the derivative equals e to the 2y minus x. And we're going to be given 0, 0 as our initial condition, and we're asked to find y. You'll have to know a little bit or remember a little bit about your algebra rules, that when you subtract powers like that, when you have e to the 2y minus x, that it's better to rewrite that as e to the 2y over e to the x. Okay? That subtraction of powers means it came from a fraction. Now we want to separate, which means all things x need to be on one side and all things y need to be on the other. So we're going to end up with dy over e to the 2y, and we're going to end up with dx over e to the x. So I just separated. Now that doesn't look good for integration, so we want to write it better. This is e to the negative 2y times dy because it's in the denominator. And on the other side, it's e to the negative x dx. That format is the way you want to write it so that you can do your integration. So this is the separation. Separation's complete. All the y parts are on the left, all the x parts are on the right. And now we're ready to integrate. When we integrate e to the negative 2y, we get e to the negative 2y divided by negative 2 and ln e plus the first constant. When we integrate on the other side, we get e to the negative x divided by negative 1 and the natural log of e times and the second constant. So we can clean that up a little bit, but we want to find c before we find y. So let's just clean this up. Let's write this as negative 1 over 2 e to the 2y equals negative 1 over e to the x plus a single constant c. All right, find c before you find y. So here now we're going to plug in 0, 0. So we'll have negative 1 over 2 times e to the 0 equals negative 1 over e to the 0 plus c. Remember, e to the 0 is 1. So we have negative 1/2 equals negative 1 plus c. Add 1 to both sides. C turns out to be 1/2. All right, now we're ready to find y, now that we know what c is. So this is just some algebra. So we've got negative 1 over 2 e to the 2y equals negative 1 over e to the x plus 1/2 is my constant. I need to work on getting y alone. So the first thing I need to do is multiply everything by negative 2. Okay, multiply everything by negative 2. This part, this is just basic algebra, times negative 2 times negative 2. That gives me positive 1 over e to the 2y. It gives me positive 2 over e to the x. And then it gives me minus 1. Then I would recommend writing this as e to the negative 2y. You don't have to do that on the other side because we're not trying to get x alone, but we are trying to get y alone. Okay, what do I need to do to both sides next to get y by itself? I need to apply a natural log on both sides. So this is heavy on the algebra. When I apply the natural log to e to the negative 2y, I just get negative 2y. And then the natural log is around the entire quantity, 2 over e to the x minus 1. And then the last thing would be divide by negative 2. So y by itself, negative 1/2, the natural log of that quantity that I applied the natural log to. Your calculus is going to be very minimal. It's going to be about 1 line of calculus. The only calculus you do is the integrate step. Everything before that is algebra. Everything after that is algebra. And so if you mess up on your algebra, then you're going to end up with an answer that's not right. Okay, I have one more for you. Okay, this notation, given d2y equals sine x plus cos x, and given 0, negative 3, and given y prime of 0 equals 1. You are given the second derivative, which means in order to get to y, you're going to have to separate and integrate twice. Okay? So that's fine. We can separate and integrate 2 times. So we're going to get, separate is d2y equals parentheses sine x plus cos x, parentheses dx. And there's basically dx2. That almost means like there's 2 of them, which is going to allow you, if the first time you integrate, you get rid of one, and the second time you integrate, you get rid of the other. I could do that on the other side if I wanted to, also dy and dy. But I'm going to integrate now. So I separated. I get rid of one of the dy's, and I'm left with that. And then I have the antiderivative. Sine x is negative cos x. Then if cos x is positive sine x. And then I have plus c. This is my first c. The initial condition I have right now is the derivative. I have that y prime, which is another way to say the derivative, when you plug in 0, should be 1. So I'm going to plug in 0 for my x, negative cosine of 0, plus sine of 0, plus my first constant, is equal to 1. So 1 equals, cosine of 0 is 1, so negative 1 plus 0 plus my first c. And so my first c actually turns out to be the number 2. Okay, so I've got dy equals negative cos x plus sine x plus the constant 2 that I just found. Now I'm going to integrate those. I'll put parentheses around it, and I had an extra dx to use. So I'd only gotten rid of one of my dx's from before. And so now I've got y equals, and the antiderivative of negative cosine is negative sine, and the antiderivative of sine is negative cosine, and the antiderivative of plus 2 is plus 2x. And now I have my second constant. And so at this point I'll use my second initial condition of 0, negative 3. So negative 3 for y, and 0 for all the x's. Plus 2 times 0 plus c2. So the negative sign of 0 is 0, minus the cosine of 0, which is 1, plus 0 plus my second c. So my second c turns out to be negative 2. And so my final answer is y equals negative sine x minus cos x minus plus 2x minus 2. And now I have y by itself because I did my separate integrate process twice.